Hello and welcome to today's webinar, Laser Plastic Welding 101, the latest evolution in joining technology. My name is Josh Brown. I'm with LPKF Laser and Electronics, and I will be your host today. Now, today's webinar is intended to be just a brief overview of laser plastic welding, so if at the end of this short presentation you feel like you would like more information, then I will give you instructions on how you can get a copy of LPKF's Laser Plastic Welding Design Guidelines document. This is a technical resource for designers and engineers who are in the concept phase of a project and they're looking to determine if laser plastic welding is a viable solution for their application. So let's go over the three main topics that we're going to cover in today's presentation. First off, we have what is laser plastic welding, and in this topic we're going to cover the basic process of laser plastic welding as well as a few of the fundamental concepts. Secondly, we're going to be talking about applications that currently use laser plastic welding as well as the industries that you'll find those applications in. And then finally, we're going to talk about how laser plastic welding can be a solution to common problems that you may face with other plastic joining methods. And throughout this presentation, we're going to refer to those as just advantages. Now, I left topics number 2 and number 3 up on the screen together because we're going to be covering them simultaneously. As we go through the advantages, I will list applications that correspond to each one of those. Okay, so let's move into topic number 1, which was what is laser plastic welding, and first off we're going to cover the basic process. Now the process involves 4 main factors. We like to call these the big 4, and you can see them listed below. Now before I jump into these, I want to give you a quick definition of how laser plastic welding works. So the process of laser plastic welding involves passing laser radiation through an upper transmissive layer down to the surface of a lower absorbing layer. Now at the surface, where the energy is absorbed, heat is created, and this heat allows the plastic to become molten, and that molten plastic creates a weld. So let's talk about how each of these 4 factors play into the process of laser plastic welding. So first up we have our transmissive upper layer. Now the main characteristic of this piece of plastic is that it needs to have the ability to transmit laser radiation. Now when we say transmissive or transparent, keep in mind that we're talking about transparent to laser radiation and not optically transparent. Now this is because laser radiation for the purposes of laser plastic welding falls into the infrared spectrum, which is outside of our visual sight range. Now a perfect example to compare the difference between optically transparent and laser transparent is the cover of this gear sensor. Now notice the top is completely opaque black, but that's how we see it. Now recall, this piece of plastic only needs to be transparent to the laser radiation, not transparent to how we see it. So this is achieved by adding very dark red and green dyes, and that gives it an opaque look, and it allows it to retain its laser transmissive properties. So factor number 2 is the absorbing lower layer. Now the main characteristic of this piece of plastic is that it needs to have the ability to absorb the same laser radiation the upper layer transmitted. Now this absorption will create heat, and that heat is what allows the plastic to become molten and create a weld. Now most thermoplastics are naturally transparent to the laser radiation, so in order to achieve absorptive properties, additives have to be used. Now typically these are pigmentations. In the case of the gear sensor you saw here, carbon black was used. This is most common because it's the best absorber, and it's also a very cheap way to achieve a black looking color. Other colors can be used, it doesn't have to be black, but like I said, black is the best absorber, and it's already a very common used pigmentation in the injection molding process. So you can see by this example, again, that the top layer, although it's black and the bottom layer is the same color to the way we see it, the laser energy reads that top layer as completely transparent, where the bottom layer will absorb the laser energy. So you can achieve different properties of how the laser is going to react to those pieces of plastic based on the types of additives that are used. Now if you have an application that requires special color coordination, such as applications you'll find in the medical industry quite often, where you need clear-to-clear welds, this is possible using special additives that will give the lower layer absorptive properties while allowing it to retain its optical translucency. So that brings us to factor number 3, which is contact between the 2 joining partners. Now it does sound relatively obvious that if you're welding 2 pieces of plastic together that they would need to be in contact, but there is a less conspicuous reason that we bring this up. Now recall that the laser radiation is absorbed by the lower layer, and this absorption creates heat. Now it's this heat that allows the plastic to become molten and create a weld. The problem you run into is that it's only being absorbed by the lower layer. So in order to get the upper layer to heat and become molten to create a weld, you have to transfer that energy from the lower layer to the upper layer. Now this is done through conduction, and contact is going to ensure that. Now, typically contact is achieved by building the parts to fit well together naturally. However, to ensure perfect contact, pneumatic clamp tooling will be used throughout the process. The final factor is material compatibility. The two pieces of plastic to be joined need to have similar resin properties as well as similar melting temperatures. If the melt temperatures of the plastics vary too greatly, then one piece of plastic may react very well to the laser radiation, while the other piece is left completely unaffected or actually burning. Now, the chart you see to the right is a listing of a few of the plastics that are weldable to each other. Now, you notice that the diagonal line that indicates that each plastic is weldable to itself, and then the pluses outside of that give you some additional material combinations. Now, this is just a very simple chart. If you would like to see a more detailed chart with weld quality as well and more plastics, then you can find a copy of that in the back of our design guidelines document, which again, I will give you instructions on how to get a hold of at the end of the presentation. So that wraps up topic number 1. Let's move into topics number 2 and number 3. Recall those were how laser plastic welding will address common problems with other plastic joining methods, and to just dumb that down, we're going to refer to those as advantages of laser plastic welding. Also, keep a lookout for the applications that will apply to each of those advantages. Now, here's a quick list of the most common plastic joining methods. We're not going to go into these in detail today. I assume that if you're watching this presentation, you're familiar with these or at least have heard of them by name. We'll just be focusing on laser plastic welding today. Now, just because laser plastic welding is a very flexible process and it can work with a lot of applications and it does have a lot of advantages, that doesn't necessarily suit it to be the best process for your particular application. The way we like to say it is laser plastic welding kind of picks up where the other methods leave off. If you have a very complex application that requires solutions that you haven't been able to find with other plastic joining methods, then laser plastic welding may be a great option for you. All right, so let's move on to topics number 2 and number 3. Now, this is the first of 9 slides you'll see in regards to the advantages that we're going to cover. You can see each of those 9 advantages listed on the left. And then notice on the right, you'll see pictures of each of the applications. Also, as these boxes slide up from the bottom, these are going to tell you which of the 3 major industries that this particular application will fall into. Just a quick note, consumer electronics, medical devices, and automotive, those are the 3 main industries that you'll find laser plastic welding in today. The major focus is really on medical devices and automotive, but consumer electronics is gaining some ground. So that being said, let's move into our first advantage, which is lowered joining costs. Now, laser plastic welding has the ability to lower joining costs compared to other plastic methods for a few factors. First off, and probably the most notable, is that there's no consumables involved in the laser plastic welding process. There's no screws, rivets, adhesives, or tapes. When dealing with mass production, anytime that you can remove consumables from the equation, you're talking about dropping per part costs dramatically. The second factor is minimal system maintenance. Now, laser plastic welding systems are very robust. They're designed to run 24/7 with very minimal downtime. I believe the only scheduled maintenance is the swap of a water filter on the cooling system for the laser. And factor number 3 is fewer failed parts. Now, this is due to laser plastic welding's excellent process monitoring and quality controls. And I'm not going to go into those right now because I'm actually going to cover those towards the end of the presentation. So let's move on to advantage number 2, which is minimal part stress. Now, laser plastic welding's main advantage when it comes to reducing part stress is its ability to create localized heat. Now, in engineering terms, you may have heard this referred to as an HAZ, or a heat affected zone. In laser plastic welding, it's going to produce a very small heat affected zone. So, to contrast the difference between laser plastic welding and other joining methods, take the picture on the right. If those 2 pieces of plastic were to be friction welded, essentially they would be rubbed together to create heat, and heat would be created anywhere that those 2 pieces are in contact with each other. Now, the problem lies in the fact that there's a lot of surface contact between those 2 pieces. What can happen is if too much heat's created, you can damage the plastics, or if there's sensitive components inside the plastics, those can be damaged as well. Now, with laser plastic welding, all of the heat is localized to only where the laser strikes the plastic. So let me zoom in on the picture. Now, as you can see, this dark area here is the laser travel path. That's the only area that's going to be affected by the heat in laser plastic welding. So excess heat won't be created anywhere outside of that laser travel path. Now, this is a huge advantage when you're dealing with sensitive applications, and for a couple of reasons. First of all, by reducing part stress, you're going to reduce the amount of failed parts you create, and you're going to save money. And then secondly, by minimizing part stress, laser plastic welding is really opening doors for new and smaller applications. So let's move on to our third advantage, which is joint strength. Now, laser plastic welding has the ability to create very strong joins. In reference to other plastic joining methods, I believe only hot plate welding can produce a stronger joint. Now, the application you see here is the housing for an electronic sensor that you would find in a car. So again, we're in the automotive industry. Now, as the automotive industry moves towards placing more and more electronics within their vehicles, the demand for robust electronics is becoming more and more prevalent. Now, as we talked about on the last slide, electronic devices tend to be sensitive. However, in the automotive industry, durability and wear are huge factors with any part that goes into a car. So having the ability to produce strong joints, even in the most sensitive applications, is becoming not only an advantage, but a requirement in the automotive industry. The purpose of this slide is to prove that laser plastic welding can produce very strong joints. So in order to do this, we're going to use what's called a pull or a burst test. In this particular instance, a pull test was used. And what we're trying to determine by this test is whether or not the weld is weaker than, as strong as, or stronger than the parent material. Now, in laser plastic welding, you'll find that most of the time the weld will actually be stronger than the parent material. However, let's zoom in and find out for ourselves. Now, this application, you can see that this white part is a lid, and this originally sat on top of this housing, and the joint would be all along the edges. Now, what we're looking for here is material transfer. So you can see black transfer here and some in the corner, and then on the housing you can see white transfer here, here, and then all along this edge. Now, what that tells us is that as these two pieces were broken apart, that the breakage occurred not in the weld, but in the parent material, and some of that material was left on each of the two pieces of plastic. So in this case, laser plastic welding did indeed live up to its name and create a very strong weld. Okay, so let's move on to advantage number 4, and that is laser plastic welding's ability to weld 3D and complex shapes. Now, the application you see here is a taillight. So again, we are in the automotive industry, and what we really want you to take notice of here is the curvature of this taillight. Now, let me zoom in, and I will trace out where the weld would take place, and it's going to be all around the edges of this taillight. Now, as you can see, the curves of that taillight are far from simple. There's double curves involved and deep height changes. Now, if you were to weld this with, say, friction welding, the height changes would create pinch points, and those pinch points would generate more energy at certain spots than others, and you'd have a very inconsistent weld. However, with laser plastic welding, again, due to localized heat, heat's placed only where it's needed, and it's very consistent. Now, this particular application also takes advantage of the TwinWeld 3D. This is a robotic arm-assisted laser source, and the advantage that it gives is that it's able to move the laser source relative to the joint. So any height changes in the application due to curves are a non-issue because the laser source is moving relative to that height. There's also one more thing I wanted to mention about the TwinWeld 3D system, and this does fit quite well with 3D and complex shapes, and that's a proprietary technology that uses halogen heat radiation in addition to the laser radiation. So there's really two clear advantages to this, the first being that the halogen heat sources will soften and anneal the plastic. Now, when you're dealing with 3D and complex shapes, it's going to be tougher to get a really nice fit between the two parts. If the plastic is softer, though, it's going to tend to fit better together. The second advantage is that the halogen lamps are essentially preheating the plastic around the laser. So the laser won't have to work as hard, or it won't take as long for the laser to melt the plastic and create a weld seam, and can reduce cycle times by up to half. So let's move on to advantage number 5, which is laser plastic welding's ability to leave no particulates behind. Now, particulate development has become a big issue in both the medical and automotive electronics industries. particulates left behind from the manufacturing process can potentially contaminate the application. Now, in this particular application, you see a microfluidic device with very small channels. Tiny amounts of fluid are passed through those, and even the smallest particulate could contaminate the desired results for this particular device. In the automotive industry, what you're seeing is devices that have circuit boards in them. Particulates can get into those circuit boards and gum them up, making them obsolete. So again, particulates are going to result in more failed parts during the manufacturing process. Now, the reason why laser plastic welding does not leave particulates is because during the process there's no frictional motion. Unlike ultrasonic welding or friction welding, the parts aren't being rubbed together. Anytime you rub two pieces of plastic together, you're going to get a scaling effect or particulates developed. And that can be seen in this example where you have a laser plastic welded joint on the left and a friction welded joint on the right. And notice the difference in the cleanliness from the laser plastic welding joint to the scales and particulates left behind from the friction welded joint. So let's move on to advantage number 6, which is precision. Now, laser plastic welding has the ability to create welds in the less than millimeter range. Now, what this means is that devices such as these below were basically made possible by laser plastic welding. So the device on the left is a microfluidic device. Something to take note of with this device is that it's no larger than your cell phone, about 3.5 inches long by 2 inches wide, and there are 2 full meters or 6.5 feet of weld seams within that very small device. And then on the right, you have a microatomizer, and based on the fact that it's sitting on top of a finger, you can notice that that is about a dime-sized device. So what this will mean is that as the medical and electronics industries look to innovate smaller and smaller devices, that more precise joining methods are going to be required to actually assemble those pieces. And laser plastic welding is really on the forefront, opening up a lot of doors for those smaller, more innovative devices. Advantage number 7 is probably the most flashy advantage, and it is aesthetically pleasing weld seams. Now, the application you see here is a car taillight, and this taillight belongs to Hyundai's flagship luxury sedan, the Equus. Hyundai put a lot of emphasis on their taillights for this car. They brought in outside designers, and their goal was to create a 3D look for the light, and they did a very good job achieving it. Laser plastic welding was chosen as the joining method because of its ability to create tight seams. Now, after determining the capability of laser plastic welding, they actually decided to use the weld in the design itself. So what I'm going to do here is I'm going to zoom in on this taillight, and I'm going to trace out all along the top here. You can see that that is the actual weld joint. And notice they didn't even attempt to hide it. It was actually used as part of the design for the taillight. Now, aesthetically pleasing weld seams is kind of just icing on the cake. So where this advantage really comes into play is where it synthesizes with the other advantages that we talked about. No longer do you have to sacrifice quality of the function in order to get quality of the form. You can have a good looking part with very high quality function. Moving on to advantage number 8, we have the ability to weld different materials. Now, we talked briefly a little earlier about material compatibility and welding different types of plastics to one another. What we're really trying to get across here is the ability to weld hard to soft. Now, this is a CV boot for a car. It's essentially a joint, and the black piece of plastic you see there is flexible, and the white piece will be welded inside of that. Also, again, along the same principles, laser plastic welding has the ability to weld soft to soft materials. So that brings us to our 9th and final advantage, which is process monitoring. Now, process monitoring gives you the ability to have a high level of quality assurance. And due to laser plastic welding's nature, there's multiple process monitoring techniques that can be taken advantage of, and we're going to go through 4 of those today. So the first technique we're going to talk about is melt travel monitoring, and there's 2 aspects to melt travel monitoring. There's the path, or what we call the melt travel or melt collapse, and then time. So essentially, as the 2 parts are heated up and compressed together, the melt travel is the amount of compression that takes place. Now, during testing, you'll determine the amount of melt collapse that's required to get a good quality weld. Also, you'll determine the amount of time that should require to take place. So you're going to have a graph that looks like this. As you set those parameters, you'll enter those into the computer, and then during the manufacturing process, any part that falls outside of those parameters will be rejected, and then again, all of that data will be recorded so you can review it. So process monitoring technique number 2 is a pyrometer measurement, and pyrometers are essentially going to measure the heat that's reflected off the surface of the component. Now, let me zoom in here on this picture. The heat map on top differs from the heat map on bottom based on this small gap right here. Now, what this gap is going to indicate to us is that this part in particular lost heat at this point, and we want to know that because we want to determine if that's a defect in the part, or if it's going to be something that's consistent throughout the entire manufacturing process. The third process monitoring technique is reflection diagnosis. Now, as laser energy strikes the plastic, some of it's going to be reflected, some of it's going to be absorbed, and some of it's going to be scattered. In this case, the reflection diagnosis technique is looking at measuring the amount of reflected light from the surface of the application. So the simplest way to explain this is that as light strikes the surface, it's going to reflect a certain amount of light. Now, if there's a gap between the two plastics, as you can see in the example on the right, then more reflection is going to happen at that point. Now, as the two pieces of plastic are welded together, as you can see in the example on the left, less light is going to reflect off of the interface of the surface. Now, the reflection diagnosis system will measure this, and it will determine if too much light is being reflected, then it can let you know if there's a gap between the two pieces of plastic. So the fourth and final technique is burn detection. What you would like to see throughout an entire process is a very consistent heat all along the weld seam. Now, burn detection is going to measure the amount of heat coming off of the surface of the plastic, and anytime you see a heat spike, it's going to let you know that a burn probably took place. Now, two reasons a burn can take place. One is if a laser is left on a piece of plastic for too long, it's going to essentially vaporize the plastic and cause a heat flash, which is kind of what you can see here with this little spike. The second way you'll see a burn take place during the process is if there's a contamination on top of or within the plastic. When the laser strikes this, it's going to burn it, and that burn will create another heat flash, and you'll see that reflected in the burn detection system. Now, you don't want to have contaminants inside the plastic, because if the laser is striking the contaminant and not the plastic, then you can get a cold spot or a heat shadow, and a weld won't be created along that point. And so that wraps up our ninth and final advantage, as well as topics number 2 and number 3. But before I conclude the webinar, I'd like to cover just a few disadvantages of laser plastic welding. So let's jump right into those. First off, and probably the most apparent, is the initial capital investment of laser plastic welding systems. Compared to other plastic joining methods, the systems are significantly more expensive, and this is often the largest barrier to a company actually taking on laser plastic welding as their joining solution. However, do keep in mind that laser plastic welding has a very low total cost of ownership. Recall what we talked about previously. There are no consumables involved in the process, very minimal system maintenance, and fewer failed parts due to the excellent quality assurance. Disadvantage number 2 is part geometry limitations. Now, every joining method is going to have their own limitations. Laser plastic welding has a few, and the most obvious is the transmissive layer thickness. We recommend a transmissive layer thickness of no more than 3 millimeters. And the reason why is because anything thicker than that, and you're going to have a tough time transmitting enough laser energy to the weld interface to create the adequate heat for a quality melt. Now, there are a couple other part geometry limitations. They're a little more advanced, so we're not going to cover them here. If you'd like more information on those, again, you can get them from the design guidelines document that I will be introducing to you here in a minute. Disadvantage number 3 is that the plastics must be optically suited. You do have to have one piece of plastic that is transmissive to laser light and one piece that is absorptive. So this does provide some limitations when you're trying to deal with certain types of plastic or certain colors of plastic. If you're very specific on the colors of your application, then this can provide certain limitations. However, do keep in mind that you are able to generate most color combinations using additives, colors, dyes, or as you saw, the clear-to-clear additive that we talked about. Disadvantage number 4 would be the tight part tolerances. Laser plastic welding is relatively unforgiving for parts that are not injection molded very well. Precise part molding is very important. Any warpage or gaps in the part can wreak havoc throughout the process and result in a very poor quality weld. And with that final note, we can conclude today's webinar. I'd like to thank you for watching, and again, as I promised, here's the information on how you can collect a copy of our design guidelines document. Now, remember, this document is designed for engineers and part designers looking to determine if laser plastic welding is a viable solution for their application. Also, feel free to use this contact information to get a hold of me for comments or questions regarding this webinar. I look forward to any correspondence, and again, thank you for coming. Have a great day.